Okay, so let's talk about, let's talk about capacitance. Now, just this weekend, it's kind of a coincidence, just this weekend, my 11-year-old son had never seen Back to the Future. So we watched Back to the Future, and of course you hear about the flux capacitor. Okay, and I'm just here to tell you that all capacitors with a charge in them have electric flux in them. So there's lots of flux capacitors out there, I guess. It's a wonderful word, and however, I hate to disappoint you, but there's no way we're going to be able to go back in time using these devices. What we're going to do is develop an idea of capacitance, and it turns out that this idea is very useful for creating a little device called a capacitor. A capacitor is a little device that stores up energy in a circuit by separating charge on two different plates and creating an electric field between those plates and having a voltage difference across those plates. So it stores up energy that we can use later for a circuit where things are happening. Now, we're still going to be looking at these devices, these capacitors, for an electrostatic condition. So again, we're not going to be looking at currents yet, but we're going to get there. I mean, we're very close to start talking about currents. Okay, so what is a capacitor? Well, we can look at the most general, blobby-looking, impractical thing possible. What if I've got a surface, an amoebic surface? I like that name. That's an amoebic surface, and I'm going to put some positive charge on it. And then over here, and I'm going to call it, so that's positive Q. And then over here is another amoeba, and it has the same amount of negative charge. Capacitance, you've got charge separation somehow. You got positive charge, you got an equal amount of negative charge. Actually, capacitors are always electrically neutral in that you've got charge separation where you got positive and negative charge, and that charge is the same amount. Okay, so the net charge on a capacitor is 0, but on one side you'll have positive and the other side you'll have an equal amount of negative charge. Now this creates an electric field around here, and using our rules for electric field, remember to draw enough electric field lines to represent the space around it, and the number of field lines are proportional to the amount of charge. They start at positive, they terminate at negative, okay, and you never cross electric field lines on pain of death. Okay, well, not really, but now here's the thing. Because there's an electric field here, and here's my little electric field out here, when I go from the negative plate and I take my little positive test charge and I work against the field to go to the positive plate, I get a voltage difference. There is a difference in voltage between here and here. Okay? And it doesn't matter where I start. If I start right here, anywhere on this conducting, let's say this is a conducting surface, and this is a conducting surface. If I start on the surface and end on the surface, I've gone through the same change in voltage. Okay, and so what I'm going to do is I'm going to say, well, I'm going to define capacitance now. Capacitance is a quantity that I am now defining. So this is by definition here, folks. Capacitance by definition is a ratio of how much charge there is on one of the plates, and we don't care about negative charge. I mean, just use Q. We just say on the positive plate. How much charge is on the positive plate? Okay? Divided by the voltage difference between the negative to the positive plate. And again, this is all regardless of sign. You can even put absolute value. There's no such thing as negative capacitance. It's just the charge on one side divided by the voltage difference to go from the negative to the positive side. Okay? Now, this ratio of how much charge you've got and how much voltage difference there is, okay, it's called capacitance. And let's take a look at the units. This has units of coulombs per volt. And a coulomb per volt, it has a name in and of itself. By definition, a coulomb per volt is called a farad. And it's abbreviated with a capital F. So we have a new quantity. It's based on quantities that we've worked with before. It's the charge on, how much positive charge you've got on one side divided by the voltage difference between the negative and positive charge. It has units of coulombs per volt, obviously, which is a farad. Now a farad, if you've got a capacitor with 1 farad of capacitance, that's a huge capacitor. Okay, you almost never see farads by themselves. Almost all practical capacitors will have, the amount of charge over here will be like microcoulombs. So you quite often will deal with microfarads, or even picocoulombs and picofarads. So you have to use those tiny little metric system prefixes with this. So you'll quite often see microfarads or picofarads when you look at actual capacitors. If you go to Radio Shack and buy some capacitors, they'll probably be measured like this. And remember, this is times 10 to the negative 6. This is times 10 to the negative 12. Sometimes you see nanofarads, that's times 10 to the negative 9. Okay. So this is a fairly simple definition. Okay, now what we're going to do is we're going to apply it to a couple of different situations. Let's take a look at a charged sphere and figure out what the capacitance is for a charged sphere. So here's a sphere, a metal sphere, and we're going to put a net charge Q on the outside. Thank you. A net charge on the outside of it. Okay, now this creates an electric field. And let's say it's isolated. So this electric field goes out, and where does it terminate? It terminates at infinity, okay, in our pretend little physics world. Okay? And, well, this has a capacitance. We can figure it out by using this definition of capacitance. Oh, by the way, we use the letter C to represent capacitance, which is unfortunate because we use the letter C to represent coulombs, which is a unit for charge. So you have to look at the context. Does the letter represent a unit? Does it represent a quantity? Okay. Now, the capacitance of this is equal to the charge on here divided by the change in voltage. Well, okay, so always start with this. Now, look. This is not that bad, you guys. And we're going to get to something, a really profound idea here. I'm going to give you the charge. So let's say it's given. Well, if this is the charge, we know what the voltage is to go from infinity, from my negative charge, was way out here by infinity. Let's put a little zigzag here. Okay, okay, we reached infinity. Congratulations. Now, how much work did it take to go from here to here? Well, this is a sphere and it has a certain radius r, doesn't it? And we know what the voltage is at the surface of a charged sphere, measured from infinity to the surface. It's kq over r, right? So the voltage difference from the negative to positive charge is just kq over r, which is very nice. The q cancels. You have, and so what you have is the capacitance of a spherical charge metal is just r, the radius, over the constant, the electric constant, K. Now, by the way, it's more common to express this in terms of epsilon naught, the permittivity of free space. So I'm going to say this is equal to, remember that K is equal to 1 over 4 pi epsilon naught. So this is going to become 4 pi epsilon naught. Whoops. Am I still on camera? Yeah. 4 pi epsilon naught times the radius. Either way, you can write it like this, or you can write it like this. Doesn't matter. But you'll see it more often written this way. Okay, now, let's take a look at this. When you have a capacitor, and there are lots of different ways of separating positive and negative charge. Here I just, up here, I just had two amoebas, okay, with positive and negative charge. And the only way I can define it is, Q over delta V. I mean, there's no way of calculating what delta V is for that. You just have to say delta V. But we're going to give you situations where you can figure out the voltage difference. And the voltage difference is always going to be a function of Q. So the Q is always going to cancel out. And your result is going to be this. The capacitance for a certain arrangement of positive and negative charge is always going to be constants of nature times the essential geometry of my capacitor. The essential geometry of the capacitor. Now, what's the essential geometry of a sphere? What's the only thing you can change on a sphere? The radius. So we have constants of nature times the radius. Okay? Now, we can do this for cylinders. We can do this for spheres. There's a lot of different variations on this. We're going to do one more, and then we'll be done. We're going to do it for what's called a parallel plate capacitor. So let's talk about parallel plate capacitors. Okay, parallel plate capacitors. That should be an O. All right. Now, these are the, in E&M, in electromagnetism, there are so many things that are named badly. But a parallel plate capacitor is perfectly named because it's just two parallel plates. Imagine I've got two plates of metal. Now, first of all, let me, and then we're going to take a wire and we're going to attach it to a battery. So here's a car battery or something. And we're going to say this is the positive terminal and this is the negative terminal. So now let me ask you, let's talk about the essential geometry here. What's the only thing? There's only two things you can change on a parallel plate capacitor. What can you change? Oh, by the way, I drew them as squares, but they can be amoebas as long as they're flat and parallel to each other. There's only two things you can change about the geometry of this. The distance between them is one. What's the other? The shape of the plate or the area. The area. Those are the two things I can change. And here's what we're going to do. We're going to drive an expression for the capacitance of a parallel plate capacitor, and we're going to find that the only thing it's going to depend on is how big these plates are and how far apart they are. That's the essential geometry of a parallel plate capacitor. Okay, well, let's give this, so this is going to have a positive charge on it, right? Now let's assume no edge effects. We're going to kind of simplify things here. This is going to create an electric field inside here. Okay, so there's my electric field, E. Now, what we want to do is go through a series of little derivations here that aren't too hard, and we're going to figure out what the capacitance is, an expression for the capacitance. Well, let's start off with the basic definition for capacitance. It's the amount of charge on this plate, we'll call it Q, over the change in voltage when you go from the positive to the negative side. Okay. Well, so let's figure out what delta V is. That's usually what you do. You figure out what, well, it's the electric field. Well, delta V, let's start off with the basic definitions because I'm kind of into that. Negative E dot ds, right? Well, the electric field in here is uniform, so I don't need to worry about the integral or the, and let's say we're going to move directly across from here to here. And so, and I'm moving against the field, which will cancel out the negative sign. So delta V becomes E times D, where D is what? The distance between the plates. Okay. Now we're running out of time, so I just want to hopefully you can see how I got easily from here to here just by going whoop. The field is uniform. What is ds? What is my total displacement? The distance across the plates there. All right. Well, dang it. I want that now. This is kind of nice because now I got Q over E times D. Now D is the distance between the plates, part of the essential geometry of this. So hey, we're making progress. But I got to get rid of Q and I got to get rid of E. Okay, that's what I want to do next. I want to get rid of the electric field. Well, what is the electric field from here to here? Well, this is a conductor. And I have a little expression for the electric field around a conductor, coming off of a conductor. And we did this one in chapter 24 when we talked about Gauss's law. It's equal to the charge density divided by epsilon naught. Now go back and review that. We did cover it. Look in your book, or I think it's posted on one of the videos. Oh, but what is sigma? That's the charge density. Well, what is the charge density? It's the total charge divided by the area. So there's Q, this plate, and here's the area of the plate divided by epsilon naught. So now I'm going to put this in here. And when I do, I get Q over the electric field, which is Q over A over epsilon naught times, don't forget the D. So here's the electric field. And we've done it. We're done. We just got to clean it up. The charge will cancel. And this, when you flip everything around, you get epsilon naught times the area. Oh, thank you. You get epsilon naught times the area, right? It flips up to the top, divided by D. And this is the capacitance for a parallel plate capacitor. This makes total sense Okay, let me back out. Let me zoom out a little bit so you can see the capacitor here. Okay, think about this. I've got a battery with a certain voltage on it. What if I made the plates bigger? Do you see that it's... What if I made the plates bigger? Well, it just leaves more room for more charge, doesn't it? If I make the plates bigger, I'm going to get more charge for the same voltage. Oh, more charge for the same voltage? That means I've got a greater capacitance. I have more capacity to store charge for the same voltage drop. Well, but what if I make the plates farther apart? If I make the plates farther apart, well, then I'm going to increase this distance, but it's the same voltage. I got the same battery, so I'm going to decrease the electric field, and the only way to decrease the electric field is to have less charge on the plate, which means I'm going to decrease the capacitance. I have less charge for the same voltage. Okay, so bottom line is this. Okay, let's see if we can take a look at the whole thing here. Capacitance, by definition, is how much charge has been separated for a given voltage difference. It has units of farads, coulombs per volt. If you have any kind of charge distribution, you can figure out the voltage. If I have a sphere with charge on it, there's my capacitance equation. And then I did the same thing here with a parallel plate, which was a little more complicated. But again, capacitance is always a function of a constant of nature, in this case epsilon naught, the area of the plate, and the distance between the plates. When I did the sphere, it was just the radius of the sphere that mattered. So, hey, do the examples, read the book, and stay caught up. As you study old material, you need to work on the old material. You're going to get left behind. That is all.